Covalent bond is formed when two or more atoms share electrons, and by definition the electronegativity difference, or END, is less than 1.7. With covalent bonds we have to distinguish between two types of bonding configuration. One of them listed here as a nonpolar covalent bond. Eventually we will see that there is a polar covalent bond. There's the polar covalent bond. So what's the difference between these two? The Earth has a north and south pole. That means the Earth is polar. It has an alignment that's different from one side to the other. When electrons share, the alignment of that sharing is not necessarily the same. The sharing can be equal between two atoms, or it can be unequal between two atoms, and that's what we're going to explore now. With a nonpolar bond, the electronegativity difference is zero. And the only time a nonpolar bond occurs is when you have two atoms that are identical. Fluorine, when it bonds to itself, there's no difference between the two atoms. They're the same. So already you can see there's no polarity there. There's no alignment. They're the same thing. They both have the same valence. Fluorine has 7 valence electrons, and if you look up here you see the same thing. We don't need to worry about the 1s electrons. We only need the highest energy level, s and p. So we have 2, 4, 6, 7. Same thing for this other fluorine. According to the octet rule, we need 8 electrons in each valence shell. This has 7, and this has 7. Well, what if they shared these outside electrons? So count them up again. 2, 4, 6, 7, 8. Now that fluorine, if it shared that electron, would have 8. And this fluorine has 1, 2, 3, 4, 5, 6, 7, 8. They both would have 8, and they'd be satisfied. The electronegativity difference, fluorine has an electronegativity of 4. 4 minus 4 would be 0. All nonpolar bonds have an electronegativity difference of 0. And then look at the electron cloud graphic. Notice how it is symmetrical. It shows you that the electrons are being shared equally across the atoms. They could be anywhere, but it's nice and symmetrical. You can cut this in half in any direction, and it's symmetrical. The electron sharing is the same. Now let's compare that to a polar covalent bond. The electrons are being shared, but they're not being shared equally between the two atoms. Let's take the example of hydrogen and chlorine. Hydrogen has an electronegativity of 2.2. Chlorine has an electronegativity around 3.2. So their difference is around 0.9 or 1, well below the 1.7 cutoff, so it's a covalent bond. But do the electrons share equally between the two atoms? Here is hydrogen with 1 valence electron. You can see that right here. Chlorine has 7 valence electrons. Here's the kernel of the noble gas neon representing chlorine's kernel. But then the valence has 7 electrons out here, 2, 4, 6, and the 7th one is bonded here with hydrogen. If you count up the electrons here, you have 7 plus 1 is 8, satisfying the octet rule. Hydrogen loses that electron, so now its outer shell is okay. This is one way of writing it. A dash means that there's a shared pair of electrons. Here's another way showing that the electron spends most of its time over here with the more electronegative chlorine. And this electron graphic shows you the same thing. The electrons spend more time on the chlorine than it does around the hydrogen. It's unbalanced. It is not symmetrical. This is polar. The two ends are different, just like with the Earth. North and south are aligned differently. Same thing here, it is aligned differently. Just as a reminder, there are 2 conditions for chemical bond stability. You need a full valence, which means the outer shell has to be complete, and you need electrical neutrality. But what happens when we have something like this? Covalent bonds share electrons. Well, with a nonpolar bond, the electrons are shared equally between the two atoms. With polar bonds, the electrons are shared unequally. One of the two atoms is more electronegative than the other, meaning it wants that electron more. It's a nonmetal. Metals want to get rid of the electron to the nonmetal. Here it's in the reverse. This would be the metal, that would be the nonmetal. What if the sharing is so unequal that one atom actually shares both electrons to the bond? That is possible, and that is called a coordinate covalent bond. When the electrons being shared between two atoms are both donated by the same atom, we call that a coordinate covalent bond. It's very similar to borrowing a book from a library or a rental video from a video store. The books or the rental video are given to you, and you treat them essentially as if they belong to you. Yet at the same time, the books are counted as part of the library collection, or the video as part of the video store collection. Look at this example. We have the compound ammonia, which is actually a stable compound. It's the stuff we use to clean floors. It smells terrible. Nitrogen has its octet rule complete with 3 bonded hydrogens. Notice here there's 2 electrons paired together, and they form a little electron cloud like an orbital. So that would have a relatively negative end to it because they're electrons. Then over here you've got a hydrogen that is actually bonded somewhere else. It gives off its electron to some other atom, like in an acid. So it would become positively charged here. Losing that electron to some other compound, it would become positively charged. Well, since that is negatively charged, that positive and that negative now come together to form an electrostatic bond. And what you have now is instead of NH3, you have NH4, but it has a positive charge. This is called a coordinate covalent bond. Here's another way of looking at it, another way of writing it. But ammonia is a very different compound from ammonium. They react completely differently. In fact, this is called polyatomic ion. So it actually will react ionically. But what holds it together is covalent bonds.